So, in the previous video, we talked about different ways of getting to the conclusion that with a separable differential equation, you can get this relationship between x and y that is a solution to the differential equation. This is the method of separation of variables. We showed one slightly hand-wavy method that involves simple manipulation, just multiplying the dx through and dividing by g of y. And then we showed a slightly more rigorous way down here that involved actually using the chain rule and showing that there is indeed this implicit relationship. Now in this video, we're going to do some separable differential equation examples to get a feel for what they look like doing in practice. So I'm again using the Fundamentals of Differential Equations textbook by Nagel, Saff, and Snyder. I'm in section 2 of chapter 2, and let's see, this is problem 8 right here. Asks to solve the equation dx dt equals 3x t squared. So, as we can see, this is indeed a separable differential equation because we have our derivative on the left here, and then we also have here a function purely of x and a function purely of t. And because we can break it up like that into these pure functions of our two variables, we know for sure that it is separable because we'll be able to divide them and get the differentials on the right side. So let's do that now. We know that we have the dx on the left, so we want to get this 3x on the left also, and you could also leave the 3 with the t squared. It doesn't really matter. So let's, I suppose, divide by just the x, because we can leave the 3 there. So we divide by just the x, and we're going to multiply by dt. So we're going to get 1 divided by x times dx. So we divided by the x, and the dt is going to go on the other side, 3t squared dt. So we multiplied through by dt, divided by x. We're left with 1 over x dx equals 3t squared dt. And now that we have all of our variables lined up with their differentials, we can go ahead and take the integral of both sides, just like we did when we were formulating what it might look like to do a separable differential equation. We can take the integral of both sides. Now, what is the integral of 1 divided by x dx? That would be the natural log of the absolute value of x. And again, we're going to have a plus c, but we're going to have two arbitrary constants. I'm just going to merge them into one on the other side. Now this natural log of the absolute value of x is going to equal the integral of 3t squared. The integral of 3t squared is 3 times t cubed divided by 3, so the 3 is going to cancel out. You're just going to get t cubed, and now we can add on our arbitrary constant. And this in of itself is a perfectly valid implicit solution. Let's say, for sake of argument, we wanted to solve for what x is in terms of t. Well, in that case, we can raise both sides to the power of e. So e to the natural log of x, e to the natural log of the absolute value of x equals e to the t cubed plus c. And this is really just a way of getting rid of the natural log here, because now what we're left with is much better. It's the absolute value of x equal to, now we can, this e to the t cubed plus c, we can use exponent properties to separate this out into multiplication. This is e to the t cubed times e to the power of c. And let's start denoting these as c1, because e to the power of c1, that's nothing but another arbitrary constant, which we can call c2, e to the t cubed. Now, one important thing to remember is, what is the range of these arbitrary constants? When we started out, c1 was any arbitrary constant. It could be positive, negative, or 0. The way we can write this rigorously, if we wanted to, is c sub 1 is, this e is the epsilon letter of the Greek alphabet, which means is an element of, which for our case means in, and then this double-lined r, which means that c1 is an element of the real numbers. These are all the real numbers, which is just a really fancy way of saying that c can be any number we want that isn't, for example, a complex number. Alright, now that we know c1 is any element of r, we have to think. Well, when we're changing it to this c2 over here, what's happening? E to the power of any real number, that has to be greater than 0, right? So we cannot actually compute, we cannot have C2 at any number less than 0, or even equal to 0, because e to any real number is never 0. So we're going to have that C2 now, C2 is greater than 0. Now, though, we have this absolute value of x. If we were going to solve for this absolute value of x, remove the absolute value, we would have to say that this now equals plus or minus C2 e to the t cubed. But let's think about this again. If we have some number that is greater than 0, but now we're offering to take either the positive version of it or the negative version of it, that's going to make this into another new constant, which we can call C3 times e to the t cubed. But C3 is going to be either greater than 0, or C3 is going to be less than 0. And the typical concise way of writing this is that C3 is not equal to 0, because that is the only value that it cannot be if it can either be greater than 0 or less than 0. C3 is simply not equal to 0. And with that, we can now say that x equals some constant, 3c, which is not equal to 0, times e to the t cubed. Now, try to think about why C3 can't be 0, and it'll start to make a lot of sense. It's because if we had followed what we were doing with our x here, we would notice we're dividing by x. And I was actually a little bit careless at the start of the video, because we have to make sure whenever we're dividing by something that it does not equal 0. So when I was dividing by x here, I assumed that it couldn't be 0, which is not something good to do. So in general, you might want to do another case, like say, okay, if x was 0, then dx dt would be 3 times 0 times t squared, which would mean that if let me do this in a different color to make it pop out more. So we would have that if x was 0, then we would get that dx dt would be a constant, which means that we just have some function x of t that is a constant. This would be our solution if x was 0. But if x isn't 0, then we have this entire range of solutions. And if we think about, again, why C3 can't be 0, then it's because if C3 is 0, then this expression for x would be 0. And it would make no sense to be solving our separable differential equation with C3 as 0, because we would be dividing by 0 up here. So I hope that makes sense. The reason C3 can't be 0 is because it would imply division by 0. But now that we have both of these cases, for C3 not 0, we would have this exponential here, and if C3 was 0, in a way we could think about x having a constant solution. Both of these are valid solutions to the separable differential equation.